ever get a speeding ticket and think, wait, how can I be going that fast if I just left the house? Today's deep dive might just equip you to win that argument, in the court of physics at least.
Right.
We're cracking open excerpts from the Feynman lectures on physics, that classic, that somehow makes even dense topics a page-turner.
It really does.
Our goal, to unpack how physicists see motion totally differently than our everyday intuition.
And trust me, Feynman had a gift for making those aha moments both profound and entertaining.
Oh, yeah.
He starts with something we all think we get speed,
Okay.
but then he throws this curveball.
Okay, let's have it.
Picture this.
Okay.
A cop pulls over this lady and says, "You were doing 60.
Huh.
And she argues, "No way, officer. I was only driving for 7 minutes. How could I be going 60 miles an hour if I wasn't driving for an hour?"
I've totally used that logic. But seriously, what's the physics comeback?
It's the perfect example of where our gut feeling about speed hits a wall.
Okay.
We think average speed over the whole trip, but that ticket, that's all about your speed at one precise moment, your instantaneous speed.
Right.
And figuring that out, well, it stumped some of history's greatest minds.
Wait, are we talking like ancient Greek philosopher level stumped?
Big time.
Wow.
Think Zeno's paradoxes,
Okay.
like the one where Achilles can never outrun the tortoise.
Right.
These guys were brilliant.
Yeah.
But even they got tripped up by trying to describe motion without the right tools.
Wow.
It's like they were playing a complex video game with only 2 buttons.
Okay, so what was the missing button that unlocked this whole thing?
Calculus.
Oh.
Now, before you hit the stop button on this podcast,
Whatever.
I promise Feynman makes it click.
Okay.
See, those Greeks, they were stuck looking at motion in snapshots, freeze frame thinking.
Right.
Calculus is like finally hitting play on the full video.
Okay.
It lets us analyze those infinitely tiny changes in speed, direction, every fleeting moment of motion.
So calculus is basically the upgrade from flipbook to IMAX for understanding how things move.
Exactly. It gives us the precision to make sense of a speeding ticket,
Okay.
to pinpoint that one instant the cop clocked you.
Oh, gosh.
One of the biggies in calculus is the derivative.
Okay.
Now, stick with me.
Okay.
In motion, the derivative is how we figure out the instantaneous rate of change.
Instantaneous rate of change. Yeah.
See, even the words sound like a brain workout.
But it's a workout with a payoff.
Okay, good.
Think of it like this.
All right.
Imagine a ball falling.
Yeah.
At any moment, it's got a speed.
Right.
But a derivative tells us how fast that speed itself is changing at that very same moment.
Okay.
Not just how fast it's falling, but how fast it's speeding up as it falls.
Whoa. Okay, so it's like zooming in on that instant,
Yeah.
seeing the tiniest shift in motion even as it happens.
That's the beauty of it. And the way we actually find a derivative is pretty cool, but maybe we should save that for after you've had your coffee, right? Yeah, I think I need a minute to process all of that. We'll be back right after this quick break. Okay, so my brain is primed for caffeine. I immediately need calculus hit me with how we actually find this derivative thing.
Well, let's stick with our falling ball visual. Feynman uses this to show how elegant the math can be. So the ball's speed is increasing as it drops, right? 1 second, it's at, say, 10 meters per second, but an instant later, it's falling even faster. The derivative is our tool to pinpoint exactly how much that speed changed over an insanely tiny blink of time.
Like, are we talking smaller than a nanosecond here? How can we even measure something that quick?
That's the wild part. We're not just measuring, we're using math to zoom in infinitely close to that instant. Imagine looking at the difference in the ball's position at 2 points in time that are ridiculously close together. Then picture shrinking the time between those points smaller and smaller until it's basically 0. The derivative emerges from seeing what happens to that difference as the time interval vanishes.
Okay, I'm getting a mind-bending flashback to high school calculus here, but I'm also kind of amazed that we can capture something so fleeting, so precise with just math.
And here's where it gets even cooler, this derivative idea. It's not a one-trick pony limited to speed. We can use it to find the instantaneous rate of change of practically anything. Temperature, pressure, even how fast a stock is plummeting, or hopefully soaring.
So it's like having this universal decoder ring for change itself. But we've been talking a lot about going from distance to speed to acceleration, basically breaking motion down into smaller and smaller pieces. What about going the other way, putting those pieces back together?
You're talking about integration. And you're right, it's like hitting the rewind button. If we know the acceleration, we can integrate to find the velocity, and then integrate again to figure out the total distance traveled.
Wait, so just By knowing how much something's speed is changing, we can rewind its entire motion. That's kind of mind-blowing.
It is. Think of it like a rocket launch.
Yeah.
We know the rocket's acceleration at every moment during its climb. Using integration, we can retrace its steps, figuring out its exact speed at any point during its ascent and how far it's traveled to get there.
Okay, now that's what I call a powerful rewind button. So we've got these amazing tools, derivatives, and integrals to analyze any kind of motion in crazy detail. But let's be honest, out in the real world, things rarely move in just one direction, right? What happens when things get a little more chaotic? It totally does. It's rare to see something moving perfectly straight in real life. Like even
Boom.
that rocket launch we were just talking about, it's not just going straight up, right?
You're right on the money. It's also traveling horizontally, and then as it gets higher, it might even start to curve.
Hmm.
Real-world motion is usually a mix of movement happening in multiple directions at the same time.
So how in the world do physicists even begin to unpack all of that? It seems way too complicated.
It might seem that way, but the beauty of physics is that we can often break down seemingly complex things into smaller, more manageable chunks. Feynman uses another great example here. Imagine tossing a ball to a friend.
Okay, got it.
Huh,
I can picture it's not just going up and down, but also traveling horizontally.
perfect. That curved path the ball makes is called a parabola, and it's a classic example of compound motion. Instead of trying to understand the entire motion all at once, we can separate it into its horizontal and vertical components.
So kind of like separating out the ingredients of a recipe?
Exactly. We can see how fast the ball is moving sideways, which stays pretty constant because there's no sideways force acting on it once it leaves your hand. And then we can look at how gravity affects its up and down motion, making it go faster and faster as it falls back down.
And here's where I'd usually get lost, but if I'm following you, we can still use those same tools, derivatives, and integrals to analyze each of those separate motions, right?
Precisely. Even though those movements are happening in different directions, the principles stay the same. We can figure out the instantaneous rate of change of the ball's horizontal speed, which would be close to zero since it's mainly moving sideways, or how much its vertical speed is changing because of gravity. It's like having this incredible set of tools that work no matter how complex the movement gets.
It's seriously cool how those concepts underpin everything around us, even a simple game of catch.
Absolutely.
Yeah.
And that's what Feynman was so brilliant at showing. Physics isn't just about equations and abstract theories. It's about understanding the magic of the everyday world around us.
Speaking of magic, we've covered a ton of ground in this deep dive. We've gone from speeding tickets to ancient Greek paradoxes to the mind-bending world of calculus, all in an attempt to understand how physicists make sense of something as seemingly simple as motion.
And hopefully our listeners are starting to see that simple motion is actually way more complex and fascinating than they might have thought.
Totally. So the next time you see something moving, whether it's a car zipping down the highway or a leaf swirling in the wind, take a moment to appreciate the invisible forces, speeds, and accelerations at play. It might just change how you see the world.
And hey, if you can use a little calculus to win that speeding ticket argument, even better.
Now that's what I call putting physics into action. Thanks for joining us on this deep dive into the fascinating world of motion. We'll catch you next time for another adventure in knowledge.